Hey everyone, Dr. Calkins. We're going to do today Experiment 7. Experiment 7 is our second and final nuclear chemistry lab. So the good, the bad, and the nuclear here. In order to do this one, we're going to use a radiation counter. These are very expensive, but they're going to use high voltage in order to recognize particles that we can't see. So it turns out in a quarter-sized piece of your skin, you can get anywhere from 30 to maybe 100 little hits of radiation from things like radon in the air that's radioactive. So we're going to prove that first in class by going over to the lab here in a minute. We're going to look at how much radon is actually in the room. We're going to count it 3 times and get an average. That'll give us an idea of how much the room is producing so that we can subtract it from all of the samples that we're about to test. So we're going to go over and get set up, and then we'll be right back. All right, so we have everything set up. So again, we need to know how much radiation is already in the room. That way we can subtract it from all of our numbers on the following pages. So we're going to count for a minute each time, average that, and that's what we're going to subtract on all the pages coming up. So here's our setup. We have our Geiger-Müller tube here. Notice underneath, very, very thin membrane here. It's a vacuum tube, so if this were to pop, it would sound like a shotgun. Very absent of air, so when those particles hit, it can recognize based on the voltage that we add to it. We do have some radioactive sources here. One of them that we'll use later is the gamma source. We have a beta source and then an alpha source. Although this alpha source, its half-life is 138 days, so several years ago when we bought this, it's probably already dead. But the gamma and the beta are still very active. We have our testing samples here for our next lab on the next page, or at least the next portion, and then there are shields down here at the bottom for another portion as well. So here's our Geiger counter. On the back, there's going to be a red button. We're going to turn that on. Right now, it doesn't have any voltage to the source at all. So we're going to have to go through our menus down to high voltage. So for that one, we go display select, high voltage. And then we're going to set this, when I calibrated this one last year, and it's still pretty close, 900 volts. So 900 volts is set, so we're going to go back for the menu up to counts at the very top. The second one is time. We're going to be doing that for you, so we're not going to have to worry about that. But counts we need, and all we need to do now is hit count. And notice our numbers are already going up. It's very random on how fast it goes up, but this is how much radiation is in the room. And notice over here, there's just air. So it's the amount of radon that can go up and under and then hit that detector. So we're going to go for a few seconds more, 60 seconds total, and come back. All right, so we hit stop and we got 23. Notice we're cheating just to line it up with our lab book. So as you check the answer key, you're going to have those mimic numbers. So record 23 seconds for your, or at least 23 counts for your first 60-second time, and we'll repeat this again. All right, here's our second background at 31. So again, we're going to repeat this one more time. So here's your second 60 seconds with a count of 31. All right, so here's our last background. We ran it and it ran 28 as an average of the class, so we're going to run with that one. Add these 3 together and then divide by 3. All right, so we're ready for the next page. The average that we got was 27, so go ahead and fill that background column in like I did. Again, you're going to subtract that every time we test the sample. So our first sample is going to be granite rock. So we're taking this granite rock and we're putting it inside. We're trying to make sure that it's nice and tall, close as we can get to that detector up top. So that's about as close as we can get. So we're going to go over to our counter again. We're going to hit count and wait 60 seconds and we'll be back. All right, so after 60 seconds, we got a count of 43. So record that, and we'll come back with our next one. All right, so we're gonna take the granite out, and these other samples have little cups, so we need to adjust those appropriately. We're gonna take this plastic shield off, because that's enough to stop a lot of radiation, like alpha particles and so forth. We're gonna kind of eyeball it, looks pretty close there. So here's our salt. We're going to come over here and hit count again. Come back in 60 seconds. All right, so in our case here, we get a count of 98, so don't forget to subtract, and we'll come back with our next sample. All right, here's a summary of our results. So again, we had granite at 43 counts, salt substitute, which is KCl, 98, fertilizer at 64, cream of tartar at 61, coffee at 29, and ice melt at 28. So every sample that we tested had a little bit of radiation over the background, saying that we can't avoid that kind of background radiation no matter where we go. It's just part of our lives. Our skin and tissue know how to deal with it. So we're going to come back for our next section with a little bit of busy work first. All right, so we saved these for a reason. This is urinal nitrate, so it's not that orange thing you see in a urinal. It's actually uranium nitrate. So we're going to put this one over here. It is a small sample, so we're going to raise this up closer to the detector, so we don't have to worry about it hitting any air molecules or anything to slow it down. And notice when we do this, as long as it doesn't fry our detector by having too much radiation, notice how fast this one's going to count. Intense amount of radiation. And what's funny about these is, depending on how high you move it, it can be substantially different just because of the amount of air in between. Those alpha particles can't reach. So notice just in a few seconds here, it's still going through the roof. This is extremely radioactive, something that you wouldn't want to hold against your skin. So you might see in the lab key that it's a fairly small number. We're going to run with one of these bigger numbers. If you go up to counts, go down to time. This is 34 seconds. Tremendous amount of radiation here. A lot of uranium was used in like carnival glass and things historically. Definitely used in power plants as well. So we're going to get up to our final 59-second count and hit stop, and then give you an accurate reading of how this machine works. Much larger than you're used to seeing. So let's go back to the counts window, and this is the number we want to record. Super radioactive, much more dangerous than all the rest. That's why it's not good to be around uranium for very long. So we'll come back with our next sample. All right, so before we test this, I'm going to show you something unique about your house. In the roof or by the doors of a lot of your houses is a smoke detector. In those smoke detectors is a detector that's battery powered. And next to that detector is a radioactive sample, and that's where I found this. This is americium-241. And it produces so much radiation to that detector every second of its life that the detector stays quiet. The only way for this detector to realize something is wrong is if the battery is low, then it's having trouble reading this radiation, so it has a specific beep. But what we use it for is if there's smoke that comes up and interferes with that radiation, the detector senses a decrease in the amount of radiation, and now it beeps again. So that's either because your house is on fire, or maybe your significant other's just burned supper. So let's test this sample now. All right, so we're going to take that radioactive sample. Little donut up is the americium inside. We're going to put it in there just like the other one. Aim the americium right at our detector. And as long as it doesn't overload it, we're going to hit counts. And notice, very radioactive. This is the most radioactive thing that you've ever been around in your life, and you probably didn't even know it. So on this one, we're going to do the same thing. Just watch it go crazy. Just to give you an estimate of the time, if we go down one, we're only at 18 seconds. And yet, on the counts, we're already up to almost 3,000. So we're going to come back when it hits 60 seconds. All right, so we're back after 60 seconds. We're going to scroll back up to counts. And 6,513 sitting in every room of your house. Still need to subtract our background. So we're going to get set up for the next section. So for our busy work of this lab, we're going to practice some nuclear reactions. So this one says write out the reactions for potassium-40 that was used in most of our samples up here. So in order to get those started for you, you want to write K40, K40. Just like down here, it's uranium-238, so 238 uranium. And then as we go to this lower one, we have the smoke detector, so our americium 241. Now we're going to see which kind of reactions they are. So this is positron and beta. So arrow, arrow. Positron would be our 0, positive 1, E. And then you need to find the daughter. Here potassium 40 again goes beta. So that's 0, negative 1. And then find the daughter. Down here with uranium, alpha, beta, and gamma. So there's no captures here. So alpha, 4/2 helium. Find the daughter. Beta, same as before, 0, negative 1. Electron, find the daughter. And lastly, gamma, 0/0, diving little fish gamma symbol. And find the daughter there. Americium, alpha and gamma. So 4/2 helium is the alpha particle, find the daughter. And gamma, 0/0, diving fish, find its daughter. So try that now. All right, so in this next section on page 35, again, we're going to subtract our background from each one. This time we're going to use strontium-90, which is nuclear fallout from a fission bomb. And what's unique about those is very radioactive, but we're using shields. And when we look at this, notice our shields are plastic aluminum 0.03, also our lead. So these three shields, same thickness. But notice the density, 0.9, 2.7, 11.3. Those ideas of thickness and density can help you in your questions later. Also, when we do this no shield experiment, this answer here is what we're going to bring down and extrapolate here. This will tell us what a 8-hour workday would look like if we were forced to be around radiation, a 40-hour work week, what that would be like, and 1 month at work if we were exposed to this nuclear fallout from, say, a bomb. So let's get set up for this lab and we'll be right back. All right, here we are ready to get this one tested. We're gonna go to our kit, it has that gamma, beta, and alpha source. We're gonna open it up and take out that strontium-90 beta set. It does have a plastic shield, so we're going to turn that upside down. Notice it's encapsulated in that plastic so it can't get on our fingers or anything like that. You can almost kind of see the dust inside there that they put in there. We're going to put it on our second level because we're going to have shields on our top level. First thing that we need to do is test it with no shield. So how radioactive is this fallout still years after these bombs were dropped? Let's go to our counter and hit count. So still super radioactive. We're gonna come back in 60 seconds. All right, again, so we're cheating so it lines up with our lab book, but 5,095 for no shield, record that now. And what we're about to do is do the exact same thing with a shield. So we're gonna take this plastic shield, letter E from our next row. We're gonna put it right above our sample, and now the radiation has to go through the shield to the detector. So let's come back and record that one. All right, here's a summary of the results to save some time. So plastic shield 3505, our aluminum of the same thickness 2468, thicker aluminum 794, even thicker aluminum 226, and then the same thickness lead, granted there's a plastic case around it, but the same thickness lead as the first two, only 48. That'll help you with your question later. So take a minute to record that data, and we'll be right back. All right, before I move on, I want to show you just a quick demonstration of what we just saw. So if we turn it on, it's just the radiation from the strontium. If we put in that plastic shield, notice the counts don't really change a lot. But if we were to replace that with aluminum of the same thickness, watch the numbers, a little bit slower. We replace it with something that is now twice as thick, still aluminum, Slower yet. Get something that is 3 times as thick, still aluminum. Now, pretty slow. Change it from aluminum. Go to something that is much more dense, aluminum density 2.7. This is 11.3 lead, and watch the counter now. Almost stops dead in its tracks. The radiation that we're probably seeing is radon in that small little gap above it. So pretty crazy how good lead is at stopping radiation. All right, so after subtraction, don't forget to bring this down and complete this busy work here. And then we'll come back to this next page. Here we're going to do distance. So in this case, we're going to use cobalt 60. So it's our gamma source here. So gamma source, it has a half-life of 5.27 years, so it's going to be good for quite a while. We're going to turn it and put it into this clamp over here. Aim it towards our detector, going the other way. So notice how it's facing, that foil's on the other side, facing this way. And then our detector goes over here. So being very careful of that membrane that's so sensitive. And then as we move next, we're going to go over here and show you that as long as they're lined up, this is like our gun, this is like our target, and we have a racetrack here, or at least a distance of 100 centimeters. And that's our first measurement. So we're going to go ahead and count and come back with that value. All right, this is 9. I went ahead and corrected it for the background already. Notice we didn't have a space for that. So this 9 represents after the background has been subtracted. So you can go ahead and record that now. All right, so we're going to move down to a distance of 75 and try it again. We'll be back. All right, so here's 75. So we see 11. Again, this is after the background has been subtracted, so you can go ahead and put that in here. We'll be back. All right, so here's our distance again. This is a repeat, but this is our 100. This is just a summary of our data. 75. Again, this is already subtracting the background. 50. 13, cut that in half, 25, 38, notice it's going up. And then for radiation to be dangerous, got to be close. So being far away from things that are radioactive is a good thing. So keeping your distance, if you have to be close, obviously those thicker, denser kinds of shields, definitely better. But this tells you that as long as you're not within 10 centimeters, you're relatively safe. But the problem with radioactive fallout, if it's a dust and you breathe it in, then there's significantly damaged tissue because now you're so close touching those tissues, much closer than 10 centimeters away. So now what we're going to do is take our data over here to our graph. This should be filled out. We already have our distances here. Since our biggest number is about 147, you can probably go each box 10 up that vertical edge. And then as you do that, you can probably start down here with 100. You're going to go up 9, 75, go up 11, and so forth. Connect your dots, and this part of the lab's done. We're going to come back for the questions here in a moment. All right, so as we look at the questions, a couple things to think about. Gamma ray is definitely the lightest particle with 0 mass versus the heaviest particle with a mass number of 4 for our alpha particles. Betas, again, with 0. But remember, betas are electrons. They take about 1,800 or more electrons to make 1 proton. So they do have some mass, just not enough to be recognizable. So as we look here, paper and skin, concrete, thick lead, aluminum, we want to know which of these shields is going to be the minimum amount needed to stop those particles. Just remember that if you're big, you're slow. And if you're slow, you're easy to stop. Doesn't mean that if you hit something, you won't do damage. But if you're big, you're slow, easiest to stop. Use that idea to help answer that one. Beta is kind of our intermediate kind of product. It's not quite as small as, say, a gamma ray, which is a high form of radiation we talked about in the electromagnetic spectrum. So this one definitely the most dangerous of the bunch. It's going to take the most densest kind of shield to help stop it. As we look at number 2, we have to go back to our data and say, was it the denser shield or the thicker shield that was more useful? Obviously, it'd be nice to have the best of both worlds, but if given one or the other, which one's actually better? If we get down to number 3, we want to do the nuclear reaction for strontium-90. So this says it goes undergoes beta emission. So take strontium-90 over here. So 90 strontium, put in your arrow, and then find your beta particle, and then find the daughter. Lastly, we want to know what is the lightest form of radiation. We have our 3 choices, because again, that's the easiest to penetrate through human tissue. Very common to use those in hospitals, cancer treatments, and so forth. So we'll see you next time. That's it for this lab.